This video is to explain the solutions for the sample problems for Exam 1 for Math 2414, Calculus 2. So let's start with number 1. Number 1, we're trying to write a trigonomic expression as an algebraic expression in relation to variable u. So we're trying to find the secant of sine inverse of u, algebraically in terms of u. So what you always want to do on these kind of problems is I use theta, that's not mandatory. Use theta to define what's on the inside of the parentheses, everything in there. Because once you will use theta to set up our triangle, and at the very end we'll be able to say, okay, then what is secant theta? Because once you have all three sides built on a triangle, you can then get any trig function you want off of it. So if you let theta equal sine inverse u, that means then sine theta, the way inverse functions work, sine theta would equal u. Now, of course, these trig functions have to be fractional, so u must be written as u over 1. So obviously just put a 1 in your denominator whenever you don't have a fraction. So use Pythagorean Theorem to build the triangle. Sine was opposite over hypotenuse. So I have a u on the opposite, 1 on hypotenuse. Pythagorean Theorem will get me the square root of 1 minus u squared on the short side, the adjacent side more specifically. So to find secant of sine inverse of u, that will now be just the same thing as secant of theta. Secant is hypotenuse over adjacent. So therefore it would be 1 over the square root of 1 minus u squared. Number 2, this is already written as a fraction, so we let theta equal the inside part, which is cos inverse of u over 2. Therefore, cosine of theta would be u over 2. And then, so cosine is adjacent over hypotenuse. So it's u on adjacent, 2 on hypotenuse. Once again, you use Pythagorean Theorem. And you'll get the square root of 4 minus u squared on the opposite side. Now, I guess I just happened to pick 2 examples where the radical was not ending up on the hypotenuse. In that case, of course, the radical will always be plus underneath it whenever it's on the hypotenuse. When it's on the other 2 sides, it will have a minus. So keep that in mind, on a test problem, the radical could be over in the hypotenuse. So once you figure out then that that's going to be the square root of 4 minus u squared, then you just basically have tan of theta, and then tangent's always opposite over adjacent, so you would have the square root of 4 minus u squared over u. Now this is a derivative problem. We want to find the derivative of sine inverse of x cubed. So we will refer to our trusty formula sheet. Sine inverse arc sine, same thing. It's basically u prime over the square root of 1 minus u squared. So this problem is pretty easy. Derivative of x cubed is 3x squared over the square root of 1 minus x cubed squared, which by property of exponents is x minus 6. So there we have our answer. That's not too bad. How about this next one, number 4, arctan of sec x. The derivative formula for arctan is u prime over 1 plus u squared, with the u being sec x. So this goes back to Cal 1. We need to know the derivative of sec, which is secant tangent. And then, so there's your numerator. And on the bottom, we just have 1 plus u squared, so it would just be 1 plus secant squared. And this one's natural log of tan inverse, or arctan of x. So the primary function we're differentiating here is natural log. Now, of course, the arctan will come into play also, but the outer function is the primary function that we're differentiating. So the derivative of natural log is basically u prime over u. I didn't write that down here anywhere, but it's the derivative of tan inverse x over tan inverse x. So du over u, basically. So we use the arctan formula, the derivative of tan inverse x. You see right below this formula for that. So it's 1 plus 1 over x squared, and divided by tan inverse x. And then right below, I just showed just a different algebraic way of writing the same answer. One's not necessarily better than the other. I don't know. A lot of times, if you're looking at answers and choices and trying to look at solutions, they might not use a complex fraction. They just might write it as one fraction, but that's not a big deal. Number 6. We have tan inverse e to the 2x, so then the tan inverse is the primary function we're differentiating here. And so the u is e to the 2x. And the derivative for e to the u is just e to the u du. So the derivative of 2x is 2, so I just put that in front. So the derivative of e to the 2x, all of it is 2e to the 2x, divided by 1 over e to the 2x, all squared. Which, that's fine if you leave it like that, but if you do simplify it if you wanted to, e to the 2x squared, because you multiply exponents, so 2x times 2 would be e to the 4x. Now number 7, now start time for some integration. Alright, so let's take a look. Sometimes, the trickiest thing about integration is choosing your u, what you need to do, but the good news is you're allowed to, you don't have to do it correctly the first time. If you make mistakes, you can correct yourself. That's why they invented erasers and whatnot, or scratch paper. You can start over. So that's now, a lot of times there'll be problems where, in fact, just to give you an example, if this denominator was 1 plus e to just the x only, I would let u be that entire denominator and get du. But we can't do that because we did, well, the last problem is good. Is the last problem or the one before? Yeah, the derivative of e to the 2x does not give you e to the x. So we got to get that e to the x up there. So the way I look at this is, what do I need u to be that will give me the numerator when I take its derivative? And u would have to be e to the x, because therefore the derivative would be e to the x dx. So you might wonder, well, okay, if u is e to the x, how do I represent e to the 2x? No problem. U squared is e to the 2x, because e to the 2x, and you put parentheses around it, raise it to the second power. Sometimes people get confused when you take e to the x squared, like so, like this, and you square it. In other words, that's not e to the x squared. It's e to the 2x. All right. Just in case that was an issue for you. And so there's how you resolve it. So a squared is 1, so therefore a is 1. Just obviously because it's 1, but keep in mind you do have to take the square root of that number. But obviously, just by mathematical coincidence, the square root of 1 is 1. So now we're set up in a nice du over 1 plus u squared. So that's perfect arctan. You have 1 over a in front for arctan, but if a is 1, then nothing happens here. So, and then u is e to the x, so it's just arctan of e to the x. So that takes care of that one. Number 8. This one's kind of interesting with this radical business here. So this one's actually is set up to be arctan, but keep in mind that that coefficient, that 3, doesn't have to be. Most problems you would probably see like 4x squared or 9x squared, where that number is going to be an integer square root. But that's not a rule. It's very common, but that's not absolutely necessary to solve the problem. So there's nothing wrong with letting u be the square root of 3 times x, because that way when you have u, then u squared will become 3x squared. So that's okay. So du is the square root of 3 dx. That's no problem. We're just trying to get variable-wise dx. So obviously the 2 it's part of the problem, but we can toss it to the outside. And then to adjust for that, I didn't show the step where you divide both sides by the square root of 3. But here it is out here, so it'll be 1 over the square root of 3. So on the outside, we'll have 2 over the square root of 3. And now let's look at the arctan. A squared is 2, so actually we have another radical in this problem. So if a squared is 2, that makes a the square root of 2. No problem. So we have 2 over root 3. And then now we have 1 over a, so it's 1 over square root of 2. Tan inverse of square root of 3x divided by all by the square root of 2. Which all I did here was just kind of combine the 2 square roots together. Yeah, if this was a handwritten test, I don't care about rationalizing denominators. For an online class, I might not use anything quite like this because the answer choices might be rationalized, but I'm not an instructor. That doesn't concern me. But usually when you look at answers, they usually, like for example here, multiply top and bottom by the square root of 6 or something. But that's it's just changing the appearance. It's not mathematically different. I mean, in other words, as far as a handwritten answer, that would be perfect. What I have right here, that would be fine. But if you did rationalize it and went square root of 6 over square root of 6, that would give you a 6 on bottom and a square root of 6 on top. Then you could reduce 2 over 6 to be 1 over 3. So you would actually have this first part would become the square root of 6 over 3. Of course, and I guess in a multiple choice format, you could just check the decimal equivalent, amongst the answers if you weren't sure. So number 9. Okay. So we have sine of x, integral sine of x over 9 plus cos squared of x. Another one that would be kind of interesting and would be more of a Cal 1 integral, so unlikely to appear on this test, but unless we were using one of our newer types of functions or something like a hyperbolic or an inverse. But on a Cal 1 test, I could have had a problem like this where it just said 9 plus cosine. And that way you would have let the entire denominator be the u, and you would have ended up with a natural log answer. But here, no, I got to look at this and go cosine squared. I need u to be something that's derivative is going to give me sine on top. So I need the u to just be the cosine itself, not the cosine squared. Because we can then just square the u to get your cosine squared. And that works perfectly. Du will be negative sine x dx. The negative is no problem. We can just toss that outside of the integral. But we got our sine x that we needed. So that takes care of our numerator conversion to du. So we just have the negative of du over 9 plus u squared. Perfect arctan. So a would be 3. If a squared is 9, you have negative 1 over 3. Arctan of cosine. U is cosine. A is 3. So it's cos of x over 3. And then our plus c there at the end. Now this next one's kind of interesting. When you see a couple of terms in the numerator like that, most likely, I mean that's why I hate to say 100% of the time, but at least as far as me asking a test question, it is you're going to split it in 2 integrals. The reason why I say that, because if you go back to even like, for example, in Cal 1, it's very possible that the numerator, even if it's 2 terms, could have been a multiple of the derivative of the denominator, where therefore it's just, u du, but that's not the case here. And in this class, I'm not trying to really test that per se. So if you see this, you're looking at pretty sure you're going to have to split it in 2 pieces. But I just want to clarify that's not a mathematical rule. Now, you split it in 2, just work with them individually. Then they become 2 separate problems. So the first one, with a 7 on top, it's going to fall right into arctan form, because you're going to let u be 7x, and then du actually just matches perfectly the 7 on top. I just wrote it as 7 over 7, but if you realize that's an exact fit, you can avoid the 7 over 7. And a would be 6, square root of 36, so it fits perfectly. So that's just straight arctan right here for the first one. And I'll just go ahead and go right down here. So the 1 over 6 comes from 1 over a, arctan of 7x over 6. Now, the next one, because of that x on top, this can be kind of tricky for students. You know, you might say, couldn't I let u equal 49x squared? You know, because the derivative would be 98x. But the rule of thumb, so to speak, is that, yeah, that's true, but if including the other added or subtracted number in the denominator, if that doesn't affect your du, you want to include it. In other words, this guy just changed the variable over to w just to have a different letter, but it's okay if a student uses u both times. So I guess my point being is the 49x squared, adding the 36 to it, still gives you the dw here of 98x dx. So therefore that means you want to have that in there with it. That needs to be included. So you have 98x, and then so we come over here, the 14 just comes to the outside. 98, because you divide both sides by 98. I didn't show that step. I usually show it in my notes pretty well, but looks like I didn't show it a lot of times here. But divide both sides by 98, so it's 14 over 98. And this just becomes dw over w, which is natural log. Oftentimes on a test, I've seen students who they'll end up with both parts of that answer being arctan or something, but no, this one's definitely natural log, because that, you know, obviously the key difference was that x in the numerator. So we have natural log of the u, which is 36 plus 49x squared, and then that reduces to 1 over 7 plus c. So there we go. That was kind of an interesting problem, you know, split it in two and two separate techniques. Now here's the classic completing the square. If you see some sort of like trinomial, and then really the 41 doesn't have to even be there to complete the square. Sometimes I'll put that in instructions, sometimes I don't, but it's just good to recognize if you see something, especially if you see an x squared and an x term together. Forget the 41. You see these two together, it's going to be complete the square. At least, well, there are exceptions to that, but in this particular exam, it's going to be complete the square. So you x squared, so half of 8 is 4. Square that 16, you add 16. And then, so therefore, to balance out the fact you added 16, you have to subtract 16. So essentially, we've converted that denominator into x plus 4 quantity squared plus 25. So now it's perfect arctan here, because you just let u be x plus 4, du is dx, a squared becomes 25, a is 5, so you have 1 over a, 1/5 arctan of u over a, x plus 4, sorry, divided by 5, and then your traditional plus c there at the end. Alright, so once you kind of complete the square and do that properly, it's not too difficult to finish it from there. Now this one's much different here. You have to watch for this little special trick here. Now notice this one has a negative in front of the x squared. Now I got to pull, because when you complete the square, you're just working with the two x terms. Don't worry about that negative 16. I had a student ask me in class one time, well, don't you pull the negative out of all three of those? No, you leave the number part alone and pull the negative, so it's the negative of x squared minus 10x. See, that changes to minus. So to complete the square, you take half of negative 10, and which is negative 5, squared, which is 25. So we add 25. So you might think it's going to be just like the last problem. Well, hey, you just added 25. Don't you subtract 25? Well, no, not in this case because of that minus in front. Because think of it this way. If I distributed the negative through the parentheses all the way through there, that would create technically a negative 25. So even though I added 25 inside the parentheses, I really added negative 25 to the entire problem because of the negative. So therefore, I add 25 on the outside. Hey, one way you can check is you can distribute the negative, combine all these terms, and make sure it equals exactly what we started with. That's the surefire way to tell. Now, for the ones that have minus, then your square is going to go at the end. So negative 16 plus 25 is 9. I put that in front. And then now we have minus x minus 5 squared. So once you go plus plus and get this set up, so that's a little tricky there, but then it's not bad. X minus 5 squared, 9 minus u squared, and perfect arcsine. So it's arcsine of x minus 5 over 3. So that was the tricky part, knowing to add twice there. So okay, the rule of thumb, if you want to kind of put this in sort of a concrete rule, we can do that. If there's a positive in front of your x squared, positive sign, you'll go plus, like the last one up here, you'll go plus, then minus. If there's a negative in front of the x squared, you'll always go plus plus. That's for sure a rule every time. This is a definite integral. I generally don't ask these kinds of definite integrals on an exam, but let's just kind of go through it real quick. So mainly, as long as we get the indefinite part right, but it's straight up arcsine. Yeah, pretty straightforward. 5 arcsine of x over, the 5 comes from the numerator. And then arcsine of 4 over 5 and arcsine of 3 over 5 are just going to be some sort of radian measure or degree measure, but usually radian measure. But since they don't translate into anything involving pi, there's no need to really go further on this. Well, here's a mistake right here I just saw. I didn't notice before. This was a definite integral, so that plus c didn't need to be there. Okay, yeah, definite integrals do not require plus c. All right. Well, I guess the point I was trying to make is, in other words, if it was arcsine of 1/2, which happens to be pi over 6 and something like that, I would have converted it then to something that's off the unit circle. But those are not going to be on the unit circle. Number 14. And let's see. This is not too bad. We haven't used the Arc Secant Formula yet, so this is good. So the straightforward, the u will be x, and then du takes care of your dx, and then you see the formula you'll have u squared, but then also u outside the radical, and then a will be the square root of 16, which is 4. Just for convenience, I've posted these formulas next to each problem, which obviously won't be that way on the test. You'll have the formula sheet, but I'm not going to label next to each problem which one to use. So I always try to instruct people to just, maybe if you want to kind of ignore what form you're looking for, is just try to get it set up in terms of u and du, and then worry about what the answer is going to be. So in other words, instead of just trying to shoot for the answer, but if that's whatever works best for you. And so now it just falls perfectly into the arc seek formula. So 1 over a makes it 1 over 4 arc seek of the absolute value of u, which is x, over 4 plus c. So that's the end of part 1 of this video.